Hello everyone, so today we're going to go over section 10.3, laws of logarithms. So we'll begin with example 1. Here we're going to evaluate log base 2 of 16 plus log base 2 of 8. So one way to evaluate individual logarithms is to rewrite them in exponential form. For example, we can write a equals to log base 2 of 16 in exponential form. So we're looking for 2 to the a power is equal to 16. And we know that a is going to be equal to 4. So using that idea, log base 2 of 16 is equal to 4. And log base 2 of 8 is equal to 3. So 4 plus 3 is equal to 7. Okay. On the second example, we have log base 2 of 16 times 8. So here we can multiply the two numbers together. So this would be log base 2 of 128. Now, 2 to the 7th power is equal to 128. So therefore, log base 2 of 128 is also 7. So the idea here is that when we are adding two logarithms together, we can instead multiply the arguments together if the base are the same. So here we have a base of 2. And we can evaluate the logarithms individually, so 4 plus 3. Or we can multiply the arguments of 16 and 8 together and then evaluate in one go. Next, we have example number 2. So here we have a similar idea, but we're dividing instead. So log base 3 of 27 is equal to 3. And of course, log base 3 of 3 is equal to 1. And here we have 3 minus 1, which is equal to 2. Okay. Now, if we instead divided the arguments, 27 divided by 3 is 9. So log base 3 of 9 is also equal to 2. And once again, the idea here is instead of subtracting the individual logarithms, we can divide the arguments if the base are the same. So those two rules are summarized right here. The product and quotient laws of logarithms. Important to note as well, what that means is if we have a product of two logarithms of the same base, so for example, log base c of m multiplied by log base, actually, let's use parentheses here. So log base c of m times log base c of n, that it is not equal to the product of the arguments. Okay. So very important to note that this is the product law and this doesn't work. Again, similarly, if we have a quotient of logarithms, so log base c of m divided by log base c of n, we cannot simply divide the arguments. C m over n. So again, that does not work. Okay, so now we can apply these laws to simplify expression involving logarithms into simpler expressions. So for example here, we can of course divide the arguments, so log base 2 of 12 divided by 3 which of course gives us log base 2 of 4, which we know is just 2. And the idea here is that neither 12 nor 3 are powers of 2, so we have to simplify and rewrite into a single logarithm in order to evaluate without using a calculator. Okay, next example, very similar kind of idea. So we have log base 6 of 9 plus log base 6 of 8 minus log base 6 of 2. So here the idea, of course, is we can multiply the arguments in the first two. 9 times 8 is 72. And then we are going to subtract log base 6 of 2, which means here we're going to divide. So we have log base 6 of 36. 72 divided by 2 is 36. And 6 squared is 36. So this also simplifies to just 2. Okay. Next up, again, similar idea. So we're going to rewrite the expression into a single logarithm first, and then we'll evaluate afterwards. So here we have log base x of 10 plus log base x of 75. So those will be multiplied together, the arguments. So we have log base x of 750 minus, and then in parentheses, those two arguments can also be multiplied together. So we have log base x of 6. Here then we will divide the arguments. So we have log base x of 750 divided by 6, which is 125. So that's step 1. Afterwards, we're going to evaluate this expression using the base of 5. So x is equal to 5, 125. So that will just be 3. Okay, so those are the first two laws of logarithms that we cover, the product and the quotient laws. Next, we are going to introduce the power law for logarithms. So here we have 2 log x, and we are trying to show that is equal to log x squared. Okay. So 2 log x is equal to, of course, log x plus log x. And using the product law from the previous page, we know that this is also log x times x, which gives us log x squared. And the generalization of this leads to the power law of logarithms. Sorry, there's a single law here. And that is, if we have a logarithm in base c, and then m to the p power, like so, we can effectively move the exponent p to the front of the expression and rewrite it as p and then log base c of m. So that's very useful, because if the exponent happens to be a variable, now we can move it in such a way that we can evaluate that variable, which wasn't really possible before. Okay, so let's look at some application of this law here. So in example 6a, for example, we have log base 4 16 to the 12th power, which of course is a very large number. So instead of using a calculator and finding out what the 12th power of 16 is, we can use the power law to move 12 in front of the logarithm as a coefficient. And then we can evaluate just log base 4 of 16, which of course we know is 2, because 4 squared is 16. And this is equal to 24. Okay. Alternatively, we could have also done the following. And that is, we could rewrite 16 as a power 4 in the argument. So this would be 4 squared to the 12th power, like so. And of course, we have power of a power, so we can multiply the exponents. So 2 times 12 is 24. So we also get 24 this way. So just confirmation of our answer using the power law. Next example, very similar kind of idea. So here we're going to move the 21 in front of the logarithm. We have log 10. And of course, if the base is not written, then the base is 10. So log base 10 of 10 is just 1. So this is just going to be 21 times 1, which of course is 21. All right. So now we're going to use a combination of the 3 laws of logarithms that we have seen in order to simplify some expressions. So let's look at the first one. We have log a plus b plus log a minus b. And here we can multiply the arguments together. So this would be log a plus b times a minus b, which of course produces a difference of squares. So we have log a squared minus b squared. Okay. Next example, we have log a minus 3 log b plus 1/5 log c. So here we can write the 3 as an exponent of b. So instead of 3 log b, we can have log b cubed. And likewise, with the 1/5 as well, we can write it as log c to the 1/5 power. And that is the 5th root of c. And then we can write this expression as a single logarithm, and that will be log a, and then the 5th root of c all over b. Cubed. Sorry about that. There we go. Okay. So notice that was a combination of the power law, the product law, and the quotient law from before. Okay. Next example, again, same thing. We're going to use the power law first. So here we have log a cubed, moving to 3, plus log b to the 1/2 power, or the square root of b, and then log c to the 5/4 power. So that will be c to the 5th power and then the 4th root. And then we can combine everything into a single logarithm. And so the a cubed and the b to the 1/2 power will be in the numerator of the argument, and the denominator will contain the c to the 5/4 power. So it's not always necessary to write it as the square root of b, for example. We can just leave it as a rational exponent. That's okay. And one more. So last one, same kind of idea. Once everything has been moved, notice that only x to the 1/2 power will remain in the numerator, and the denominator will contain both y squared and also the z. So like so. So this example allows us to see how multiple logarithms can be combined into a single one, which can help us evaluate them in some cases. In the next example, we're going to do the reverse, and that is we're going to take a single logarithm and expand it. So in this case, we have individual logarithms of x, y, and z. So let's see how that works. First one, notice that both x and y are in the numerator, whereas the z is in the denominator of the argument. So if we were to expand, then we have log base 5 of x plus log base 5 of y, and then minus, using the quotient law, log base 5 of z. So next one. So here we can rewrite the cube root of x, of course, as x to the 1/3 power. And then now we can use the power law to move the 1/3 in front of the logarithm. So we have 1/3 log base 7 of x, just like that. Next example here. Again, we're going to be rewriting. So here we have log base 6 of x to the -2 power. And then we can use the power law to move the -2 in front of the expression. So here we have -2 log base 6 of x. All right, and finally, the last one, probably a good idea to separate everything out first, like we did in example A. So here we have log x cubed minus log y, because it is in the denominator, and then minus log the square root of z. And afterwards, we're going to use the power law to rewrite our exponents as coefficients. So here we're going to have 3 log x minus log y. And then instead of square root of z, this would be 1/2 log z. Alrighty. So next example. Here we are given that log 2 is equal to x, log 3 is equal to y, and we're going to rewrite each logarithm in terms of x and y. Okay, it's better to just go over an example and see how this works. So for the first example, here we have log 6, which of course we can rewrite as log 2 times 3, which of course is the same as log 2 plus log 3 using the product rule. And we know that log 2 for the purpose of this question is equal to x, and log 3 is equal to y. So this is just x plus y. And that's the idea for this question. So the next part, very similar kind of idea. So here we have, instead of just 2 times 3, we actually have 2 times 3 times 10 to make 60. So when we split this up, we have log 2 plus log 3 plus log 10. First two parts are just like in the previous example, we have x plus y, of course. And the third part, notice that we are not given the base. So once again, the base is 10, the common logarithm. And log 10 is just 1, since 10 to the first power is equal to 10. So we have x plus y plus 1. All right. Let's keep moving. Next up, we have log 18. So again, same thing. We want to rewrite 18 in terms of 2's and 3's. So 18 is 2 times 3 times 3. So this would be, of course, log 2 plus log 3 plus log 3. And so we will just have x plus y, or alternatively x plus 2y. And finally, the last example of this type, 3.6. So we can rewrite 3.6 as 36 divided by 10. So that will give us log 36 minus log 10 using the quotient rule. Now 36 is 6 squared, so we can rewrite log 36 as log 6 squared, and then minus log 10, just like that. We can then use the power rule to move the 2, so we have 2 log 6 minus log 10. From before, we know log 6 is equal to just x plus y, so we have 2 and then x plus y. And of course, also from before, we know that log 10 is just 1. So we have 2 x plus y in parentheses minus 1. Okay. And that's it. So moving on to the next example, there are a lot of different ways that the laws of logarithm can be made into questions, and we're trying to cover as many types as we can, so hence the many examples from today. Example number 10. So here it says, evaluate the expression without using a calculator. So let's see what we can do with this one. So this is clearly just an application of the quotient law. So we have log base 5 of 1,000. And then both the 4 and the 2 will be in the denominator. So we have log base 5 of 1,000 over 4 times 2. And of course, 4 times 2 is 8, and 1,000 divided by 8 gives us 125. So essentially, we just have log base 5 of 125, and that is 3. Okay, so what about example 10b? So here, we can evaluate first log base 12 of 12 is just 1, so we have 2 times 1. That's good. And here, minus log base 2 of 6. Nothing doing there yet because 6 is not a power of 2, of course. And then we have log base 2 of the cube root of 27, because this can be rewritten as 27 to the 1/3 power, which of course is the cube root of 27. And of course that's good because 27 is 3 cubed, so we can simplify it there. And that will be log base 2 of 3. Okay, so from there we have 2 minus, and in this case we can multiply the arguments together using the product law. So this will be log base 2 of 18. And that's it. So there's no further simplifying that could be done, unfortunately. And it says to evaluate without using a calculator. However, since 18 is not a power of 2, we can't really do that here. And so that's all we can do with example 10b. Okay, so one last law of logarithm, and it's called a change of base rule. So we've mentioned this before when it comes to estimating certain logarithms. So for example, we saw earlier with log base 2 of 18, and if we were to try to find a value for that, we probably would have done log 18 divided by log 2 using a calculator. So the change of base rule is the idea behind why we can do that. So the change of base rule says log base b of x is equal to log base a of x divided by log base a of b, where, of course, since a and b are both bases, they have to be greater than 0 and not 1, and x is an argument, so it has to be positive. So those are the restrictions. And so one of the more often used application of the change of base rule is how we can use a calculator to determine approximate values of logarithms. So here we have log base 6 of 100. So we can rewrite this as log 100 divided by log 6 using the common base of 10. And if we were to put this into a calculator, we get an approximate value of 2.570. Okay. Which makes sense because if we think about it, 6 to the second power, 6 squared is 36, but 6 cubed is 216. So if we were to write 100 as a power of 6, it will be somewhere between 2 and 3. On the right-hand side, very similar idea. So this would be, of course, log 2 divided by log 3. And this will give us an approximate value of 0.631, which again makes sense because 2 to the first power is 2, and 2 to the, actually, right, so 3 to the first power is 3. So in order to write 2 as a power of 3, the exponent has to be less than 1. Okay. So one last kind of example here. We have a couple of expressions, and we're trying to show that the left-hand side is equal to the right-hand side. So kind of an identity type question. Keep the sides separate for now. Okay. So here on the left-hand side, we can rewrite log base a of b using the change of base rule as log b over log a. And similarly, the second logarithm, of course, we can write as log c over log b using the change of base rule and the common logarithm. And on the right hand side, we can rewrite the expression as log c over log a. And we can realize right away that the log b's will eliminate each other, and so the left hand side and the right hand side are the same. Okay, so second one, we have 1 over log a of x plus 1 over log b of x, and we're trying to show that is equal to log a times b of x. So this one's a little bit trickier. But again, we are going to apply the change of base rule here. So the first expression, we will have log, sorry about that. Let's see here. 1 over, and then log x over log a. Okay, second term on the left hand side, we can again expand and rewrite as 1 over log x over log b. The right hand side, similar idea. We can rewrite that as 1 over log x over log a times b, or just ab. Okay, so to simplify the expressions on both sides a little bit, we're going to take the reciprocal of each term. So here we have log a over log x plus log b over log x. And then on the right hand side, log ab over log x. And of course, idea here is we're adding log a and log b together, so we can multiply the arguments. So this would simply give us log ab over log x on the left-hand side, which is what we want. And that's it. So as we can see here, there are 4 laws of logarithms that we went over: the product, the quotient, the power rule, and also the change of base rule. So there are 4 total, and many different kinds of questions, 12 different examples in total. So a lot of variety. But that's it for today. So once again, thank you for listening.